Hello, Chem 19 students. This is Professor Medyo Anagila. And in this video lecture, we're going to proceed on with Chapter 4.3, Redox Properties, particularly on the last redox diagram, the Pourbaix diagram. The Pourbaix diagram is a potential E pH diagram. So it tells about the stability of a metal as a function of potential and pH. This is a representative figure for the Pourbaix diagram. So it's just a part of the big Pourbaix diagram for ion. So this is usually constructed from the Nernst equation and the solubility data for the element containing the species. So in the Pourbaix diagram, those at the bottom are considered to be the reduced forms, and those at the top are considered to be the oxidized form. So we can see over here that each region is represented by conditions of potential and pH under which that said form or species of the metal or the element is thermodynamically stable. So this is an electrochemical phase diagram for redox active substances, but take note that it does not tell us anything about the kinetics of the reaction. So no rates are derived from the diagram. Since this is a representation of the electrochemical nature of the element in aqueous system, we need to take into consideration the practical stability region for water. So this is indicated by the red line over here. So this is the practical region of stability for water. So within that practical region, we're seeing the important transformation for the metal or for the element of interest. But beyond that, so above this red line over here, or below the red line, it is the water molecule that breaks down and not the metal. So for this case, the top line is actually represented by an equilibrium, which equation is listed as so oxygen plus 4 H plus proton plus 4 electron to give you water. So this is the reduction of oxygen. The bottom line is represented by the equilibrium 2H plus 2 electron to give you hydrogen gas. So these are the important equations representing the equilibrium on that border of the practical region of stability. So beyond this top line, so basically water now will break down and liberate oxygen. So we have liberation of O2 and acidification, because the reverse process now will be more important. So water will break down to give you O2 plus 4H plus and 4 electrons. So basically water is oxidized to O2. Beyond the bottom line, so as we can see there, we have the liberation of H2. So this equation will become very predominant and H2 will be liberated, and since H plus is being depleted into the medium, so we have alkalization. So it becomes basic. So the thermodynamically stable region of water at 1 atm is in between the top and the bottom line. With that, how do we further interpret the figure? So we have here regions of stability. So the stability region can be designated as immunity. So in the immunity, this shows the thermodynamic stability, and usually this is the pure metal itself. Unfortunately, in this segment of the Pourbaix diagram that I have, that region wherein immunity is shown is not presented. So it is way below this one. So over here pa. And then we have corrosion. Corrosion region is in the active state. Okay. So the immunity region is in the noble state. So the corrosion region is in the active state. So when we say it is in the active state, it is in the ionic form. So what we're seeing here actually are two corrosion region for iron. The Fe2 plus region, so this region over here, actually if you extend this, and this region over here, these are corrosion state or corrosion region for iron. So this is not the elemental state. And then lastly, the passivity or passivation region is when the region we're in, the metal has been oxidized, but it forms, particularly if we're talking about the surface of the metal. So the surface of the metal oxidizes, but it forms another solid that tends to inhibit further corrosion. So that solid usually takes the form of oxide, hydroxide, hydrides. And we say it is passivation because it prevents further corrosion of the metal surface. So for this case, the region of ferric hydroxide is the passivation region. Further information that we can gather from the Pourbaix diagram, again, this is potential and pH relationship. So when we talk about potential, we know that this deals with gain of electron, loss of electron, so electron transfer. But if it is pH, this is more closely related to proton transfer, so acid-base reaction. So in the diagram, we can clearly define which region the electrons transfer predominate and which region the proton transfer predominate, and there are also regions wherein both are actively in play. So looking into the horizontal line, so when the two species are separated by the horizontal line, this is a redox reaction. So an example of that would be this part. So redox reaction, as we can see, it separates iron 3 plus and with or from iron 2 plus. So this is a purely redox reaction. And we can represent the equation there as, so we're going in as reduction, half reaction by convention. This is how it is written. 2 plus, so you can put AQ plus electron. And the potential here is whatever this line is. In the textbook, this is roughly around plus 0.77 volts. So that's a purely redox reaction. Now, if we're gonna go to the vertical line, so this one is a purely vertical line. This is a purely acid-base reaction. So as an acid-base reaction, there's no electron transfer. So that means the oxidation state of the metal is still the same, but protons are added or removed. Okay, so it is a proton transfer. So we can see it's the conversion from ferric Fe3 plus to FeOH3. So the equation that we can designate there would be this one. So it should give you FeOH3 solid. Okay. And what's is in the medium that will give the hydroxide that is needed to precipitate out iron 3 as ferric hydroxide? That would be water. As I mentioned in the previous slides, as long as you're within the practical region of stability, you're not breaking down water here. So water, so plus H plus. So balance it, we have 3, so EQ. Okay? So you can just check the pH, whatever that pH is. I think it's about maybe 3, pH 3. Iron 3 plus will precipitate in aqueous solution as ferric hydroxide. And then we have the diagonal or the slant or the sloping lines. This one. And if you check, for example, between these two, clearly we have both redox and acid-base reaction that are in interplay. So for this case, we can represent the line, or we can represent the reaction as follows. Okay, so that's the reaction that is involved within that diagonal or sloping line. So we can see that H plus is in interplay and electron is in interplay. Actually, in this region, you can see in the equation that maybe H plus, hydroxide, or electrons are involved. Not or, and electrons are involved. So this region or that sloping line is actually, you can use the Nernst equation to determine the potential. So the slope of the line is equivalent to negative 0.0592 volts divided by whatever the pH is, multiply by the number of H plus that are involved and the number of electrons that are involved. So you can see, based on the Pourbaix diagram, that iron is actually not very stable in water, or iron metal is not a stable form of iron in water, because you can see that the region of immunity, iron metal, is not found within the practical region of stability. So it is quite favorable for iron. So when you expose iron to water to be oxidized to give you iron 2 plus and iron 3 plus. But take note that if you vary the pH, it actually forms the passivation region. So you tend to coat the surface with ferric hydroxide, and that prevents further corrosion. So the Pourbaix diagram is an important diagram that environmentalists or corrosion chemists actually take a look into. And with that, this ends our discussion for the Pourbaix diagram.